Hi, everyone. Welcome to this talk. My name is Kun Zuo from the University of Sydney. I would like to talk about supercurrent interference in field mode nanowire Josephson junctions. So this figure here tells the main topic of this talk. Basically, we studied the critical current modulation and oscillation as a function of B magnetic field. So the reason why we want to study the Josephson junction in a nanowire system is that because Josephson junctions made out of nanowires have many different properties. For example, the nanowires are small, but they still have a few transverse modes. They are very clean, weakly disordered. They are quasi-ballistic. And then indium marsenide or indium antimonide nanowires, they have very strong Rush-Bar spin-opt interaction. And now if you apply a magnetic field to your Josephson junction, then you can also bring the Zeeman interaction into account. And since we apply a magnetic field, so the magnetic field can actually thread through the cross section of the nanowire, can also bring the optical effect into the system. So therefore, the Josephson effect or Josephson currents in such a Josephson junction will become more complex, because the whole effect is a complex interplay of several parameters. Therefore, it's very crucial to understand a system like this for the future application, for example, to detect or to create Majorana fermions. So the system we use is actually very simple. So we have an indium antimonide nanowire lying on top of prefabricated electrical gates, which are used to control the chemical potential of the nanowires. This indium antimonide nanowires has a very large defect around 50 and a spin-opt energy around 50 micro eV. So the nanowires are then contacted by two superconducting contacts made of niobium titanium nitride. The reason why we use niobium titanium nitride is because their critical field is very large, larger than 10 Tesla. So here is a figure of the typical IV curve characterization of a Josephson junction. We can clearly see that the nanowires are open up gradually as we increase the gate voltage, and finally open up to a multi-mode regime. And then first thing first, we want to confirm that we have superconductivity of a created Josephson junction in this device. And indeed, we measured a nanowire supercurrent around a few nanoamps. Importantly, but not surprisingly, the supercurrent is actually gate tunable. Well, at around 1.5 volts, we are in the multi-mode range transparent regime where the supercurrent is the largest. Let's say that's the major focus of the study we're going to talk in a few slides. Right. So the B magnetic field is applied along the nanowire in the future study. All right. So first, I want to show the magnetic field dependence as a function of gate voltage. So basically, the supercurrent starts to oscillate as a function of magnetic field. You actually can see the start with a few nanoamp supercurrent, and it goes down quickly to less than half nanoamps. And then there's a node here, and the supercurrent goes up a little bit, and it starts to go down again, and almost disappears at this point. Now, if you change the gate voltage by only 20 millivolts, okay, so the gate is actually indicated here by the red line, and you can see that node changes quite dramatically. So instead of only one, we have 1 and 2 and maybe 3 here, right? By keep increasing or keep changing the voltage on the gate, you see the supercurrent oscillation is also keep changing. All right, so at 60 millivolts, we can see the first node almost goes to 0, and then the supercurrent revives and then goes down to 0, almost 0 again, and then goes back again, right? So the change of the chemical potential, right, is quite small compared to the 15 milli EV mode spacing. So what we change is not that might be kind of subtle to the whole supercurrent interference. Not only in the B magnetic fields, we also investigated the gate dependence of the supercurrent at the different magnetic field. As we can see that supercurrent is indeed very sensitive to the gate voltage. As you can see that if you take a line cut, right, a different gate voltage, yeah, you will get very different supercurrent behavior as a function of B magnetic field, right? So I want to point it out, this observation has been measured in multiple devices over very wide gate ranges in a multiple mode regime, right? And also because we didn't particularly taking care of tuning the device into so-called topological phase or topological regime, I don't believe we have any topological or region of the supercurrent oscillation in this behavior. Right? So in order to understand the mechanism of the supercurrent interference, we developed our theoretical model. Basically, we write down the effective low energy Hamiltonian by taking into account the momentum, the Zeeman field, and then spin-optic direction or spin-optic field. So we basically take the time bending approach and try to do the numerical simulation using a software called Quant. This is a typical picture of a quant where you have superconductor, superconductors in blue, and the nanowire is in red. And then we also take the opto field into account in this numerical modeling. So here is the numerical results. So in a single mode nanowire Josephson junction, if you only take the Zeeman effect into account, you can clearly see the Zeeman-driven 0 to pi transition. Well, you see the supercurrent start to oscillate at a very low magnetic field, and then oscillates several times before dying. And then if you check the phase of the system, you do see the phase goes from 0 to pi and go back to 0 and pi again, right? But now if you introduce a spin-opt interaction into the system where you protect the spin pairing, the 0 to pi transition driven by Zeeman then is suppressed. Now, if you add the orbital effect into account, the supercurrent behavior changes again. So supercurrent start to lower as you increase the B field, so more interference start to get into play. Right? Now we add disorders, then supercurrent become very small and also starts to have more modulations or oscillations. Now, if you go from single mode to 6 mode, which is more realistic for our case, and then you can see that you can still see the Zeeman, the Zeeman-driven 0 to pi transition if you don't have any other parameters in the model, but you can clearly see the 0 and the pi and the 0 and the pi again. Now, by taking Zeeman, spin orbit, and disorder into account, then the supercurrent behavior is more or less like what we have observed in the measurements I showed before, basically the B dependent and the gate dependent of the supercurrent. So, so in order to then we try to compare our numerical simulation with our experiments, which the main data is shown here, while we plot all the supercurrent behavior as a function of magnetic field at the different gates experimentally, but then we also simulated the results theoretically as a function of B and gate voltage. So I would say the results, the theoretical results and the experimental results have very good qualitative agreements by taking the more realistic parameters, for example, G factor 50, spin optic energy 50 micro EV, mean free path 160 nanometers, diameter of the nanowire 100 nanometers, and then junction length 650 nanometers, and 100 millikelvin temperature with the 6 transverse modes. Here I want to have a very short conclusion. Basically, in the study that is shown, we measured a supercurrent up to 2 Tesla over 1 micron long Josephson junction. Well, we have observed many different nodes and kinks, and I believe the predominant reason for that is the supercurrent interference. But of course, the pi and phi zero junctions might still occur, in a device that occasionally gives some nodes, but sort of embedded into the whole nodes and kinks plethora. So in the future, I would say we want to in the future the research direction will be to focus on the single mode nanowire devices. So previously we were not able to achieve a single mode Josephson junction with relatively large supercurrent. But now I think it's the fabrication technology becomes better, the contacts become better. You have the architectural grown contacts on the nanowires in the single mode. It's becoming more reachable, and then if we can make device like that, the physics of Josephson junction with different parameters, interplay of different parameters will become much clearer, let's say. All right, another thing that I would like to say, the take-home message of this talk, of this understanding with 1D nanowire supercurrent interference, is that it is very important to distinguish the interference effect from the supercurrent reentrance. So indeed, sometimes we do measure the so-called typical 0 to pi junction transition pattern, but eventually we figured out it's more caused by the interference effect by measuring more devices, exploring the more gates and B-field spaces. Well, what I want to extend the talk a little bit is that I want to discuss a little bit further about the supercurrent reentrance claimed in 2D systems, for example, in 2DECs and then graphenes. I just want to pick up a few examples. So for example, in 2019, there's a Nature Communication paper where they measured the supercurrent reentrance, or they call it supercurrent reentrance in the antimony quantum well 2DECs, right? So they have very low disorder, and then they clearly observed they get tunable nodes at a different magnetic field, and then they concluded this 0 to pi transition. Well, there's another paper working in a different system, basically indium arsenide quantum well. They also observed clear nodes, and nodes are clear nodes, and the nodes are actually get tunable, right? And then on top of that, they even measured pi phase shift after implementing squares in the system. They confirmed they attribute the supercurrent reentrance as a transition of S-type to P-type superconductivity, right? Yet another paper in Nature Physics 2017 basically explained the supercurrent reentrance, claimed the supercurrent reentrance for a different mechanism. They still have clear nodes, gate tunability. All right, although I mean there are many, the explanation, the mechanism might be right, valid, but I still want to provide an alternative explanation. Basically, it is supercurrent interference. For example, in one of the measurements not showing here in our investigation, is that we also observed a very typical pattern of a 0 to pi transition. Supercurrent goes down to 0, goes up again, and dies, and then go down and then up again. Very typical Zeeman-driven 0 to pi transition, as also shown in a numerical simulation. Right. So this clear nodes actually makes we believe that we measured the 0 to pi junction at that time, until we, did more investigation. We figured out it is caused by supercurrent interference. And then also one of the devices that we measured twice, we cooled down twice, second time, and then adding a, like a microwave IF line to do the Shapiro steps to figure out if we really have the component of a 0 and a pi. Basically try to measure the pi shift or pi component of the Josephson junction. And if you look at the results, right, you indeed can see the pi components become stronger and stronger as you decrease the magnetic field going through the node. or the supercurrent itself is less good after warming up, but after introducing the IF lines. So what I want to say is that if you only look at two figures, you only look at even the pi phase shift, right, in your measurement techniques, you would easily conclude it's 0 to pi transition. But in the end, it might be a little bit different, right? Although, in 2DEX, you only have single subband because the second subband is very high, right? You don't really consider a lot of supercurrent interference, and also because the 2DEX is much thinner than the nanowires, so the optical effect is not that possible, right? However, so 2DEX, right, is pretty long, few micrometers. And then they are very large. We cannot guarantee, right? It's just so uniform across everywhere, right? As long as you have variations in the 2DEX positions, the magnetic, the wave functions can pick up different phases at a different location, and then you apply high magnetic field, the supercurrent interference can still happen, right? That just provide one possible alternative explanation to the 2DEX system. I also want to say that try to claim supercurrent reentrance, we have to be a little bit more careful, even with the squared measurement of the phase. High magnetic field can also affect on the squared itself, right? Not only in 2DEX, but also in graphene, supercurrent reentrance was also measured and reported. So here the system is, of course, a little bit different. It's clean, right? It's actually the supercurrent re-entrance happened at very large B fields. Naively, we'll think that because the singlet pairing shouldn't survive to that high magnetic field, so they should just break, right? So we call it the unconventional superconductivity. It might be just singlet triplet coupling, Cook pairing transition, right? But on the other hand, right, back to nowadays, it's already become very clear, right? The 10 nanometer thick niobium-titanium nitride resonators, if you measure the resonator quality factor, Q internal, at 6 Tesla, around 6 Tesla, the Q factor is still very, very high. That means we still have the singlet Cooper pair pairing at 6 Tesla, about 10 nanometers thick niobium-titanium nitride. There's another paper, similarly, also measured a very large, a very good Q factor, up to 5.5 Tesla. Actually, that film is even thicker. So what I'm saying is, if you have, we have a graphene, right? Depend on the thickness of the graphene. So if you align the field very well, the magnetic field or superconductivity can survive at very, very high magnetic field. So I'm not surprised if you have superconductivity around 10 Tesla in a graphene system. Well, again, right? So first of all, the singlet pairing can survive, possibly, right? And then on the other hand, right? So graphene is not really totally flat, right? They still have, some sort of like ripples or wrinkles, depend on how you make the devices. So across a large distance, right, larger junction size, if you have a few nanometers of variation at a field of 8 Tesla, you will still be able to see the interference of different wave functions that it gives the behavior of supercurrent reentrance. Now, of course, this is my speculation, right? You can't just exclude this because of the possible, like ripples. But of course, I can't confirm that it is supercurrent interference caused the reentrance current. But in general, I would like to say that there are many, many different possibilities. There are many simpler possibilities, explanations for the supercurrent reentrance. But in order to make the physics clear, right, we have to investigate more or take more parameters or mechanisms into account so that we can rely on a more well-understood model, but not a simple model to explain the supercurrent or any other physics in our study, right? With this, I would like to acknowledge my collaborators on the supercurrent interference in the nanowire Josephson junctions. Experimentally, I collaborate with Vincent Marek, Sergei Frolov mainly to finish this paper. Theory was developed by Bas Nijholt and then Pickling mainly. And then the nanowires were grown by Diana Charles, Sebastian Blissard, Eric Backers in TU Eindhoven. And we have all the support from other people, Daniel Zambati, David van Woekron, Junten, Attila Asti, Leo Gavenhoven, and then Vyacheslav and Anton for the theory. Right, so with this, I would like to thank you for your attention, and then I'm happy to have further discussions with you if you're interested in the supercurrent interference in 1D or in 2D systems. Thank you very much for watching the video.